Okay, 9.1 parametric equations. It says we've been looking at graphs of one equation with two variables, typically x and y. Now we're going to look at equations with three variables that will represent a curve in a plane. In the rectangular equation, we are able to determine where the object is located at a point x, y, but with the addition of a third variable, often t for time, we're able to determine when the object was at a certain point. So for parametric equations, if f and g are continuous functions of t on interval I, then the equation x equals f of t and y equals g of t are parametric equations, and t is the parameter. It says you can sketch the curve of a parametric by substituting its values for t. So in this first example, it says sketch the curve with the following parametric equations. X of t equals 2t, y of t equals t squared minus 1, with t between -1 and 2. So what it's saying for us to do in order to find x and y is that we'll simply just plug in some value of t, so let's say -1, and we'll plug it in to each of the t values in x and y. So for example, -1 plugged into 2t would be 2 times -1, which is -2. And then -1 plugged into y of t means I have -1 squared, which is +1. +1 minus 1 is 0. Okay, and we would do that for each of these values. Okay, so if you want, you can pause and try to find those values yourself, or I'm just going to start filling them in. Okay, so these are all the corresponding xy values for each of the t values. Okay, notice that this is x and y, so I can actually take these and write it as a point x, y, and plot it on the graph below. So I'm going to do that now. So -2, 0 would be the first one. Then I'm just continuing and plotting the rest. Okay. And notice that all of these points, if I was to connect them, is forming a parabola. Okay, which means that the rectangular equation to these parametric equations is going to be represented by a parabola. Okay, we can also do this on Desmos. So let's say you wanted to graph this on Desmos. Okay, the most important thing here is when you're typing in your functions to make sure to use capital letters. So make sure you do capital x of t, type in the equation, capital y of t, type in the equation, and then on the next line, you would type in x of t, y of t, and then what's going to happen is an interval is going to pop up. And so I'll show you off to the side over here, and let's see if, here we go. So here's my x of t. Notice how this is like capital X. Then I have y of t. Notice that this is my capital Y of t. Here are the two graphs. And then on this third line, I have x of t, y of t. Notice both still capital. And when I typed that in, the interval popped up. So I was able to type in from -1 to 2. So if I unselect the first two, I am left with just the following parabola, which matches up with the one that I found by hand. So the curve of the parametric equation. So now I'm just going to look at these examples. So keep in mind that everything on this first page of notes is just a recap from pre-cal, so hopefully none of this is too confusing. If so, I'll definitely revisit those concepts before continuing. So it says to find the rectangular equation when you're given the parametric equation, eliminate the parameter t through substitution. So notice it gives us the same equations, and in order to eliminate t, what we're going to do is we're going to use x of t, and we are going to get t by itself. So x is equal to 2t, which means t is equal to x over 2. Then we're going to take that x over 2 value and plug it in for the t in the y equation. So I'm left with y is equal to x over 2 squared minus 1, which simplifies to 1/4 x squared minus 1. That would be my answer. Okay. Notice that this is also the equation for the curve that I found above. Okay. Another important thing about these parametric equations is notice that this is not necessarily a function. This is just telling us the direction that this curve is going. So if you wanted to, you can note that, okay, we started here when t is equal to -1, and then as we progress, this is the direction we are going. Okay. And then number 3 says, given the parametric equations, x of t is equal to 2 cosine t and y of t is 2 sine t, eliminate the parameter. So for this one, it's going to be a little different because notice we have our trig functions here. So in order to solve this, we need to remember this very important identity, and that is sine squared x plus cosine squared x equals 1. And so what I ultimately need to do for each of these equations, x and y, is to get cosine and sine by itself. So I have x is equal to 2 cosine t, so cosine of t is equal to x over 2. And then I have y is equal to 2 sine t, so sine t is equal to y over 2. And then anywhere I see a cosine and a sine, I'm just going to plug in x over 2, y over 2. So I have y over 2 squared plus x over 2 squared is equal to 1. Okay, this is the same as saying y squared over 4 plus x squared over 4 is equal to 1. Simplifying this further to get rid of those fractions, I get x squared plus y squared equals 4. So for this parametric equation, notice that it formed a circle. So now moving on to the calculus part of parametric equations, and that is us learning how to find the derivative of these equations. So the derivative of a parametric equation, what we're trying to find is dy dx. So dy dx is going to be dy dt divided by dx dt. Okay, where dx dt cannot equal 0. Makes sense, it's a fraction. Okay, all you need to know is that this is the same as saying y prime divided by x prime. This is the same thing. Okay, where x prime cannot equal 0. So we're taking the derivative of the equation y, then we're taking the derivative of the equation x. So looking at number 4, we need to find dy dx, and so we do the derivative of y. So first I'm just going to distribute the 1/4 in, so I have 1/4 t squared, and if I take the derivative of that, I'm going to get 1/2 t divided by the derivative of x, so t to the 1/2, which becomes 1/2 t to the -1/2. Okay, I can simplify this because the 1/2s cancel out, and I'm left with t divided by t to the -1/2, which I can simplify to be t times t to the +1/2, which is equal to t of 2 over 2 times t of 1 over 2, which is equal to t to 3/2. I went ahead and just showed all the steps because I saw that there was some confusion in class today, so I just want to make sure you see all the steps. Okay, so number 5 says given x of t is equal to e to the 2t and y of t is equal to cosine t for t greater than or equal to -1, find the equation of the tangent line when t is equal to pi halves. So since it wants us to find the tangent line, what we're really finding is the point slope form. So that y minus y1 is equal to m times x minus x1. So what we need to do first is plug in pi halves into x and into y. Okay. So we have x of pi halves is equal to e to the power of 2 to pi halves, which is equal to e to the pi. And then y of pi halves is equal to cosine of pi halves, which is 0. So what we just found was x1, y1. Then we need to find dy dx, and so that's the derivative of y, which is negative sine t, over the derivative of x, so 2e to the 2t. Okay, solve that at pi halves, so I'm going to plug in pi halves here. And so negative sine of pi halves over 2e to the 2 times pi halves, okay, which is equal to negative 1 over 2 times e to the pi. And again, this gives us our slope. And so if I do y minus y1 is equal to mx minus x1, then plugging everything in, I get y minus 0 is equal to negative 1 over 2 times e to the pi times x minus e to the pi. And that would be my answer.